So we're going to be looking at solving problems involving objects that are in what we call static equilibrium. What static equilibrium is a fact that you have an object that is not in motion at all. It's totally stationary, but there are multiple forces acting on it. So as an example, you're told in example 1 that you have two forces acting on an object. One is 280 newtons and it is 40 degrees south of east. And you have a second force which is 600 newtons and it is 30 degrees north of east. And they're all acting on an object. And then you're told something about a statement regarding a thing we call an equilibriant. A single force that is required to keep an object in static equilibrium is called the equilibriant. So we're asked to find the equilibriant force. So in other words, if you had these two forces acting simultaneously on an object, what is the third force that would be needed to counteract or to balance those two forces? And the basic strategy you're going to be using in all of these static equilibrium problems is that if you have an object in static equilibrium, then the amount of force total in the x direction must be 0, and the total amount of force in the y direction must be 0. We always want to think in terms of components here. Now, in order for us to decide what that missing force is going to be, we have to take those two vectors and break them into their components. So in this particular example, we have 280 newtons and it is 40 degrees south of east. So this is 40 degrees, and it is 280 newtons. I'm not going to put the units for the force. We know that force is newtons. What you have to do is find an east and a south component of that force. We also have 600 newtons that is 30 degrees north of east. So this is 30 degrees, and it is 600 newtons. So I'm just going to double check my diagrams given what happened earlier. 280 newtons, which is 40 degrees south of east, looks fine. And then 600 newtons north of east looks fine. I'm going to give everybody a couple of minutes here to determine all of the components. So you need to determine an east component of the 600 newton vector and a north component. You need to determine an east component of the 280 newton vector and a south component. And getting back to Andrea's question about, does it have to be done a certain way? I would say the only thing that's important here is you can find the values of those components. That is all that is important. So I'm going to go ahead and start my calculations and write down the numbers. So I'll pause there. For the 600 Newton vector, I got 519.6 newtons east, and I got 300 newtons north. And I think we're okay with that. For the 280 Newton vector, I got 214.49 east, and I got 179, call it 180 newtons south. We're okay with that? Okay. So don't forget that these are not the only two forces acting on the object. We need to find a third force. But what we are going to do when we solve this problem is we're going to take those two forces and find a total horizontal and a total vertical. So far, the total x can be found, and the total y can be found. This is not a total, this is just the total of those two. When I take a look at my two horizontal components, they're both east, so I'm simply going to add those numbers together. 519.6 newtons east plus 214.49 newtons east is going to give me the horizontal force that these two forces exert. So 519.6 plus 214.49 gives me 734.09 newtons, and that is east. When I look at my y, I have 300 newtons north and 180 newtons south. So now I'm adding two vectors that are in opposite directions, which means I subtract the magnitudes. I'm going to take 300 minus 180, which gives me 120 newtons. And this is going to be in the direction of the greater force, which is north. So what we have done is we have taken the forces that are acting on the object that we know about, broken them into horizontal and vertical, and consolidated the horizontal and consolidated the vertical. Does anybody have any questions in getting to that point? All right. Now, don't forget what I said. It's over here. I'll highlight it for you because I finally got my highlighter going here. What we said is that an object is in static equilibrium if the net force acting on the object is zero, but the only way the net force can be zero is if the horizontal force adds up to zero and the vertical adds up to zero. And there are algebraic ways to do this next step, but I think it's simpler to just use common sense. That if these two forces that are acting that we know about result in 734 newtons to the east, our equilibrium force must contain 734 newtons to the west. Let me repeat that. I got a little distracted for a second. If these two forces have a net east value of 734.49, then our equilibrium force must have a horizontal component of exactly that same number of newtons, but it has to be west to cancel out with the east because an equilibrium has to cancel out. If the total vertical forces that these two forces exert is 120 newtons north, then the vertical component of the equilibrium must be 120 newtons south. So the equilibrium is always opposite to the forces we've collected so far. If you just take a look at what I've got here, if I were to add all of the x's from the first two and the x of the equilibrium, I get 0. And if I were to add all of the y's of the first two to the y of the equilibrium, we were going to get 0. So the bottom line is these two forces can be used to find the magnitude and direction of the equilibriant force. And we're back to the adding two vectors tip to tail that are at right angles to one another. This is going to be probably in your first lesson in Physics 30. We'll have a problem where you end up having to add vectors like this. They won't be forces, they'll be something else, but it's something that you need to know how to do. So what do we have? 734.49 west and 120 south. And as I said, finding the answer from here should be, well, like stealing candy from a baby. Should be easy. And I haven't really talked to this class about this. I use this analogy a lot in my math classes. What you do with high school physics and math is you take a problem and you turn it into something that's easier. So Taylor is asking, are the two vectors supposed to be opposite for the equilibriant? And the answer is yes. If your total forces horizontally without the equilibriant give north, then your y component for the equilibriant has to give south, because we want the force to reduce to zero to keep the object stationary. If the two forces that are already acting on the object have a net east value of 734 newtons, then the third force to keep the object from moving must have that same 734 newtons, but it must be in opposite direction. So yes, this is the case that these two things should be opposite to each other. Did I answer your question, Taylor? Perfect. You're welcome. So now, just finding the hypotenuse and the angle, I don't think I'm going to write anything down here. We've got 120. We have to square that plus the 734.49. We have to square. Now we have to take the square root. So the equilibriant must have a magnitude of 744 newtons, and the direction can be found by taking inverse tangent of opposite divided by adjacent. Which gives us a very thin 9 degrees south of west. So the answer to this example is 744 newtons, 9.3 degrees south of west. Any other questions of clarification with example 1? Oh, okay. And if you carry all the decimals, which you should on a numerical response on an exam, it's apparently 734.1. You'll find that as we go through this online phase, I'm going to be cutting a lot of corners. That means taking some shortcuts to try to whittle down the time. I want to leave you with as much time as we possibly can to get practice. So yeah, it rounds a little bit differently if you carry all the decimals. All right, example 2. So we have a sign that's suspended by a couple of cables. One of the cables is attached to a brick ceiling or a brick overhang, and the other cable is attached to the brick wall. And I guess I should talk about this notation. This notation here, I'll write it out so I can refer to it a little better. F sub T sub 1 is called a force of tension. Tension in physics is considered a force. And I'm going to highlight that force. It's drawn on your diagram, but it's not drawn very prominently. This is the tension in that cable. That is the force that the cable is pulling on the sign with to keep it from falling. And there appears to be a typo here. That's easy enough to fix. I'll fix it in green. This number 1 should be a 2. So you have Ft1, which is the force of tension or the tension in the first cable, and Ft2, which is the tension in the second cable. So that should say Ft2. And looking ahead, I probably copied and pasted in some other ones. I'll just check. No, I don't even have it. That's okay then. Okay. Sorry, I just want to change this one as well. All right, now there is a really complicated algebraic way of doing this, but what you need to understand, and I'm going to go to the big diagram here, what you need to understand is that all of the horizontal components and all of the vertical components have to each reduce to 0. I'm going to repeat that and say it a better way. Any vertical components added together of the forces must reduce to 0. Well, there is a vertical component acting on that sign, and the vertical component acting on that sign is the force of gravity. There is a force of gravity acting on this sign. And if we go and look at the question, you're told the force of gravity is 4,500 newtons. So we can actually put that in the diagram. Now, when I look at the other forces, everybody, this force has no vertical component. So Ft2 doesn't have a vertical component. It's not going to be able to counteract any of the 4,500 newtons down. When we look, however, at this force, there is a vertical component to it, and the vertical component can be drawn there. Now, I admit I'm choosing to draw my vertical component first rather than horizontal, but I'm doing that so that you can see something. And what you can see is that this 4,500 newtons down must be exactly equal to the vertical component up provided by cable 1. If I were to look at only the vertical components here, the only vertical components acting on the sign are these two. That's it. What that means is we know the vertical component of tension 1. And the rest of the problem becomes a trigonometry problem. I'm going to pull off of that diagram only the forces acting on cable 1. So cable 1 is at a particular angle, and there is a vertical component and a horizontal component. The vertical component is 4,500 newtons. And there's no work to be shown here. There's no formula to use. There's no algebra to use. What we are saying is the 4,500 newtons down, provided by gravity to the sign, has to be balanced by 4,500 newtons up. And the angle is 55 degrees. So you can determine the tension in cable 1 by finding the hypotenuse of this triangle. The hypotenuse will be the tension in cable 1. Let's do that. Just looking at the triangle, 4,500 is opposite to the 55. The hypotenuse is what we're after for the tension in cable 1, so I can write sine of 55 degrees equals opposite over tension 1. Now, what I've done here is I wrote T instead of F, but that's kind of standard practice. You can write T for a force in a cable. When I rearrange this, I get the tension in the cable equals 4,500 over sine of 55. So the tension in that cable is 5.5 kilonewtons, or 5.5 times 10 to the 3 newtons, or 5,493 newtons. I don't care about how you report it. T1 is that number. This is the one type of problem in Physics 20 that it almost is approached as a puzzle. There's no formula, there's no set of rules that you follow. Now, if you take a look at my diagram here in the top right corner of your screen, even though it doesn't look like it in the main diagram, we have two other forces that must be equal to each other. This force to the left and this force to the right must be equal in magnitude, otherwise the sign would accelerate in the direction of the greater force. So if we can find this component, we will have found the tension in cable 2, and we will have finished the question. And now it's just a matter of using that triangle to find that horizontal component. You could use the Pythagorean theorem here now because you do know the other two sides. In fact, I'm going to do that. You could go back and do a trigonometric calculation, but I'm going to take the hypotenuse squared minus 4,500 squared and take the square root. I will write down in a second what it is I'm doing here so that you can see it. But you get 3,150, 3,151 for this component. So what I did there is I took the hypotenuse, which was 5493, I think. I'll double check. Yeah. Squared, that's equal to the 4,500 squared plus my unknown x component. Plus my unknown x component squared. So I have to take 5493, subtract 40 squared, subtract 4,500 squared, and then take the square root. And that Tx is what I have written down over here. This is the tension in the cable that's horizontally exerted. But since, I know I keep repeating myself, but this is the basic idea. Since the horizontal components have to add up to give 0, if cable 1 provides 3151 newtons to the left, cable 2 must provide 3151 newtons to the right. So the tension in cable 2 is 3151. Any questions with example 2? All right, let's take a look at the last example, which is example 3. A very similar type of question. We've got 185 newtons of tension this time in the horizontal cable. So let me approach this, now that we've done the first example, let me approach this in a slightly different way and just really cut to the chase. We have a force exerted on the sign to the right by the cable that's horizontal. We have an equal force exerted to the left on the sign by the angled cable. Why do I know that they are equal? Because the sign is in static equilibrium. We have a force of gravity acting on the sign downwards, but we must have an equal force of gravity acting upwards. So just to be sure here, and clear, what we are talking about is that this force upward exerted by cable 1 is equal in magnitude to the force downward exerted by gravity. This force to the right exerted by the horizontal cable must be equal but opposite to the force to the left exerted by the angled cable. And now what we're going to do is the following, and you need to watch this as I do it. Now what we're going to do is basically move this over here to produce a right angle triangle. And the tension in the cable that's at an angle is represented by this. So let's put in the information that we know. We know the green vector because you're told it was 185 newtons is the tension in the horizontal cable. So this is 185 newtons, but that means this is 185 newtons. Now, you're asked to find two things, the tension in the cable at an angle. Well, that's the hypotenuse of this triangle. So we need to get an angle in here. And the angle down here will be 40 degrees. If that is not clear, I'm going to mess up this diagram to make sure you understand how I know that's 40 degrees. I'm going to create a very bright pink triangle. And the top left angle of that pink triangle is 40 degrees. But that means that the bottom right angle of that pink triangle is 50 degrees because in a right triangle, the two acute angles, the two angles that are not the 90-degree angle, have to add up to 90. But that makes the angle next to the 50 degrees 40 degrees because they must add up to 90. So I'm not able to see your faces to judge your understanding of this, but listen carefully. If you find the hypotenuse of that triangle, if you find the length of that red line, using the information, you will have found the tension in that cable. If you find the bluish colored component of that triangle, you will have found the force of gravity, because the force of gravity is equal to that. So this is really the vertical component of that vector in that cable, but it's the same as the force of gravity. And this is the tension in that cable. So we just have to find the two pieces of that triangle. The physics was setting up this diagram. Let's see, in that triangle, I'm going to work on the opposite side first. I can use tangent of 40 degrees equals opposite, which is the y component, over adjacent, which is 185. So the y component of that vector is going to be 185 tan 40. Which gives me 155 newtons. And that means the force of gravity is 155 newtons. We're going to be seeing this idea a lot in this unit, where if we want to find the value of something, we find the value of something else because that other thing is the same as what we're trying to find. I know that sounds weird. Now to find the tension, I'm just going to use the Pythagorean Theorem. So if I take my vertical component squared plus my horizontal component of the tension cable, which is 185, and it appears as though I wrote degrees for that 185. It's obviously newtons. And it's 185 because the horizontal component of the other vector is 185. We have to square that and then take the square root. We will have our final answer. So I get for the hypotenuse of that triangle 242 newtons, which means the tension in that cable is 242 newtons. That image you're looking at right now is key to understanding these hanging sign problems. You know, what are the actual forces acting? I'm going to really mess this up now. The actual forces acting on the sign are this force, and this force. Those are the three forces acting on the sign. But that's not helpful. So what we do instead is we say, well, this force downwards is a vertical component, so I highlight it. This force here has a vertical component and a horizontal component, so I highlight them. This force is entirely horizontal, so I highlight it. So I only look at the horizontal and vertical components. And I know what would happen if you looked in a textbook. What you would see is you would see it drawn this way. You might even see it drawn this way. But the principle is the same. Equal up and down, equal left and right. Does anybody have any questions with that final example? Okay, so I really am going to do my best to plan the time here so you have significant period of time. Had I not, tripped and fallen on my face earlier with the first lesson, you would have at least had a half hour here left. As it stands, you have 15 minutes until 11 o'clock. Even though officially the class ends at 11, which means you're free to leave then, I will always be here till 11:30. Well, always. There's exceptions, right? But I will be here till 11:30. If you happen to look up at your screen and you see a message written that says back in 5 minutes, that just means I went to go make a cup of coffee or I just needed to take a little break. So I hope that everything went well on your end. If you do have some issues with the technology that are getting in the way, like they're almost insurmountable, please send me an email so that we can try to work it out. I think I've got most of the kinks worked out of the system at my end. So I'll let you guys get to work and I will be here. If you need any help, let me know.